So I'll hand over to Martin, who will introduce our first speaker.
Thanks a lot, Graham. Well, folks, the first speaker in this two-event meeting is John Singleton. Example A. John, little known fact, John actually turned down a place at Durham in 1978. I'm just saying to you how many of my friends seem to have done that, actually, one reason. There must be a good reason. Anyway, it was only Hatfield, so that doesn't really matter, does it? Okay, that's insulting half the audience. Then John went on to Oxford, where he was at St John's, and he was there for, he stayed on to do a DPhil there. Then went to work postdoc at GEC, and then subsequently at Phillips, so that was between Wembley and Red Hill. And then he went on to work at the High Field Magnet Lab in Nijmegen, which is really where I first came across John many, many years ago. In, I think, about 1990 or thereabouts, John moved back to Oxford, and John became the physics don at Corpus, which is a very fine college. And he was there until about 2002 or thereabouts. And then he left to go to Los Alamos, which is where he presently works. John has interest, I got written down here, fingers in many pies. Catholic interest is probably, no, better not say that. Yeah, lots of interests, all sorts of things. They range from the development of supraluminal sources, would you believe, which are working, and incidentally, using one of these items, they've been able to model the way that the Crab pulsar works over about 16 orders of magnitude or something. Frequency. Sorry, 16 orders of frequency, so extraordinary activity that. And that actually brings John into contact with colleagues here as well in Durham. As I say, very wide range of interests. Organic magnets is another one. The actinides. And today he's going to talk in the first of these two talks this afternoon, measurements of cuprate superconductors at the National High Magnetic Field Laboratory. Over to you, John.
Thank you very much, Martin. So I'm at the National High Magnetic Field Laboratory's Los Alamos campus, and like the talk later in this afternoon, we are a user facility, and so the measurements that I'll show you have involved lots of people who are both instrument scientists at the National High Magnetic Field Laboratory, like Neil Harrison and Chuck Wilkie and Ross MacDonald, and also users who come and do experiments at our facility, like Peng Chin Dai, Ed Yellen, John Cooper, and various people from all over the world. We are an international user facility. This is our organization. The main laboratory is at Tallahassee in Florida. It's part of Florida State University. This is the magnet lab itself. This is the place where we make large, steady magnetic fields. We have a 50 megawatt power supply, which gives us the electricity to make 45 Tesla in a hybrid magnet. This is the largest steady magnetic field available at the moment. This is the base of the hybrid magnet. It's about as 2.5 times as tall as that. My head.
Yes, turn your mic on.
Oh, I'm sorry. I talked so loudly that I didn't notice the difference.
It's for the record.
Is that better? Right, yes. Okay. This thing is about 3 times as high as this particular picture, so my head would be about here if I was standing on the ground. We also have a campus at Florida, at the University of Florida, where we do high ratios of magnetic field over temperature using dilution refrigerators, and we do MRI at very high fields of things like complete frogs and rats and things like that. In Los Alamos, which is the third campus of the magnet laboratory, we have a very, very large generator. This thing here, it's a 1.4 gigawatt generator from a mothballed nuclear power station. We use this as an energy storage system. We also have large capacitor banks, and we make pulse magnetic fields of 65, 75, 90 Tesla using magnets like this. And we also have 200 Tesla destructive magnetic fields where the magnet blows itself to pieces, but the sample survives. So I'm going to give an example of the use of these facilities today in studying the high temperature cuprates. So I'll give you a very brief introduction to these superconductors, the high TC cuprates, discovered about 20 years ago. And there's been an awful lot of work done on these materials, including a lot of very, very unconventional theories of superconductivity. So the question I'm going to try to answer is, are cuprates, these high temperature superconductors, like conventional metals in any way? Now, as this is a general audience, basically I'm then going to define what a conventional metal is. It's a substance with a Fermi surface. So this is what's a Fermi surface. This is my next topic, and then I'll show you how we use high magnetic field to measure Fermi surfaces to detect whether a substance is behaving like a conventional metal or not. And this involves using effects called the de Haas, van Alphen and Shumnikov-de Haas effects. Then I'll go on to some of these high temperature cuprate superconductors that we've studied using these high magnetic fields. And what we'll see is that we do actually find a Fermi surface. So in many respects, the high temperature cuprate superconductors are like conventional metals. Then there are various technicalities which result in the sort of Fermi surface that we actually measure. I'll explain those. And I'll also show how these are reconcilable with the measurements of other techniques. And finally, I'll give you some speculations. This is an experimentalist speculating about some sort of conventional mechanism for high temperature cuprate superconductivity. So, a brief introduction to these things. This is a typical yttrium-barium copper oxide superconductor, the structure, and you can make substitutions of the various metals that are involved. For example, praseodymium could go in instead of yttrium. You can vary the amount of oxygen that makes it into there. But the basic thing about these, the basic important fact is that these are layered materials. They're quasi-two-dimensional materials. Their critical temperatures, as discovered about 20 years ago, can approach 100 Kelvin. And so this led to vast speculation about flying trains worked by liquid nitrogen and things like that. And you can tune these things over a wide range of carrier densities using structure. By varying the structure, you can make different numbers of layers of these things. And you can also do things like muck around with the oxygen doping. And this gives us a varying hole density in here. This is a very simplified generic phase diagram of these things from Brooks and Schrieffer's recent textbook. Basically, this is temperature with absolute zero at the bottom. This is hole doping, hole concentration per unit cell. We have antiferromagnetism down at low numbers of holes. And then finally, as we increase the number of holes, we get this superconducting region here, with the top of this dome being something like 100 Kelvin. So these temperatures of superconductivity, the critical temperatures for superconductivity of around 100 Kelvin, are much higher than those of conventional metals, which tend to be restricted to less than 20 Kelvin. So the first thought when these things were discovered was that they're exotic in some way. They have some unusual form of behavior going on in there. So there are many theories out there in which the charge carriers in the cuprates are assumed not to be conventional electrons in solids. For instance, Phil Anderson has produced a lot based on spin charge separation. There are various things like bipolarons have been proposed. These are not conventionally behaving electrons in metals. So what we have to do with our high field measurement is to test how accurate these theories are, whether they do represent reality, or whether the cuprates are in fact ordinary metals just behaving a little bit more in a strong arm fashion than normal metals do. So, this is the question I seek to answer. Are cuprates like ordinary metals in any way? Ordinary metals are also known as Fermi liquids, and they have electrical conduction understandable in terms of mobile electrons. Metals are things where electrons are free to move. But, as I've said, many theories of cuprates involve exotic charge carriers, bipolarons, spin charge separation, d-density waves, all sorts of funny vocabulary out there. And the purpose of our measurements is to see if the cuprates are like ordinary metals or they're funny in this sort of way. So the first thing we need to understand is what defines an ordinary metal. And this is the Fermi surface. So what is a metal? How do we get a Fermi surface? An early definition of a metal by Sommerfeld was this metal in which there are mobile electrons, electrons that are free to move. Around about that time, or just afterwards, quantum mechanics came along. And, of course, the energy of the electrons that are free to move then has to be quantized. The motion of the electrons in solids is defined by things called bands. energy dispersion relationships, energies versus wave vector quantum numbers. This is a very simple band. Here we've got wave vector along the bottom, we've got energy up here, and the band is a parabola. So for instance, the bands that the early workers in metals worked with were things which just look like free electrons, but with a different curvature because of a thing known as an effective mass. Rather than having the mass of the free electron here, we have a mass which depends on the solid that we're going to work with. Now, why is this important and why does it lead to a Fermi surface? Well, this is not actually a continuous band of states, it's a set of quantized states. There are discrete states in this thing that looks like a continuous curve. And the Pauli exclusion principle only allows us to put two electrons, one spin up and one spin down, in each of these wave vector states. So let me replace that with a map of quantized K states. If we go with this dispersion relationship, the minimum energy is going to be at the middle here, and then as we work outwards in K, we're going to get larger and larger energies. So let's imagine that we have a solid which is empty for the time being. This is its dispersion relationship. This is a map of the K states. What we're going to do is put in electrons. So we first put in a few electrons. They occupy the state's nearest zero wave vector. That gives them the lowest energy. So they fill up this band to this sort of height here. We put in a few more electrons. They fill out the states up to this sort of energy and fill up the band a little bit more. Put in more electrons. Gradually the band gets fuller as we work away from K equals 0. So basically what we've done is we filled the band up when we put all of the electrons in the solid up to an energy called the Fermi energy, this thing E sub f up here. This is our band now filled with electrons. Because we've also occupied the states with lower wave vector, we filled up a surface in K space, which, and the outer boundary of that is represented by electrons that have an energy that is this Fermi energy here. So this Fermi surface is our definition of a conventional metal. A metal is a substance with a Fermi surface. I have no idea who coined that, but many people have used this in their textbooks like Kittel. So why is the Fermi surface important? Well, in a conventional metal, like copper and things like that, the Fermi energy is around 10 electron volts, or tens of thousands of Kelvin. And even when we have zero temperature, this is a picture of the Fermi surface of copper, we have these very, very energetic electrons around which are on the surface of this thing. The reason being that all the states below them in energy are full. So even if they cannot get down to any lower energies because of Pauli exclusion principle. So for a conventional metal like this, most of the properties can be understood by these electrons. For instance, if you take a set of keys and you try to squash a key with your bare fingers, the metal in the key is resisting this pressure. It's actually the electrons at the Fermi surface that are resisting this pressure. If you work out the bulk modulus of this gas of fermions, it accounts for most of the bulk modulus of the metal. So if electrons were not fermions, basically metals would be little pools of sludge lying on the floor with no rigidity or no bulk modulus. So now this Fermi energy is much greater than the temperature as well. So the properties of the metal are determined by electrons with energies approximately equal to the Fermi energy. The reason for that is that this energy is so much greater than the temperature, so thermal excitation can only populate and depopulate a tiny fraction of states either side of this. Moreover, for an electrons in a solid, the velocity, the group velocity, is given by the gradient in K space of the energy. This is like d omega by dk equals the group velocity that you know from elementary wave mechanics. The velocity, therefore, is perpendicular to constant energy surfaces because it's parallel to a gradient in energy. It's perpendicular to constant energy surface. Now, all these velocities of the electrons at the Fermi surface are going to be determining the conductivity. So therefore, the shape of the Fermi surface determines our conductivity in a metal. So basically, most of the properties of a metal can be understood in terms of its Fermi surface, a conventional metal. Now, just a little bit of terminology. To keep vocabulary simple, I will be referring to things called quasiparticles. This is a generic term for electrons in a solid. We can also get electrical conduction in solids due to holes, empty states, and almost full band. And to keep things simple, I will refer to all of these possible charge carriers in a solid as quasiparticles, but they basically behave as fermions. Now back to the cuprates. Basically, the structure is such, it's a layered structure, that all of the action from an electronic standpoint goes in the copper-oxygen planes. And we expect the bands, those dispersion relationships that might give rise to a Fermi surface if this is a conventional metal, or like a conventional metal, will be two-dimensional in character. So, what we now need to do is to look at our expectations for a measurement of the Fermi surface to see if cuprates are like ordinary metals in any way. So, first of all, the measurements of Fermi surface that were in the literature up to about a year ago were done by a technique called ARPES, angle resolved photoelectron spectroscopy. What this does is we take in a high energy photon, it kicks the energy up, kicks the electron up from a low energy, and then we get a recombination event which results in the electron being emitted from the solid. So we get the electron coming out from the metal, and because the states where the states which determine the electron's emission are determined by the Fermi surface, we can use this technique to map out the energy versus K relationships of the quasiparticles and therefore measure the Fermi surface. So the early expectations as to what this technique might reveal came from tight binding band structure calculations of the Fermi surface of the cuprates. Now in the previous overhead I said that these things were two-dimensional, so I'm going to be looking just at projections into the two-dimensional plane. And in this plane the Fermi surface just looks like this blue pocket here. It's like a slightly squared off thing. Now this is the other thing that's in this diagram is the unit cell of K space, of wave vector space, this red thing here. Because a system like a crystal is periodic in real space, it's also periodic in K space. So if we get a Fermi surface here, we expect to see its replica at equivalent points in K space. So we have this Fermi surface that straddles the corner of the Brillouin zone, which is the unit cell of K space. We see replicas of it all around here. So in an ARPES experiment, we'd hope to map that out. So what the ARPES people do is they basically scan the wave vector of the electron along this region of the Fermi surface and hope to see it. So these are some mapping out paths of an ARPES experiment by Shen et al. What you would hope to see if it was a conventional metal is that there will be a big weight of emission at the Fermi energy, at the Fermi surface. So we'd expect to see a bright band of high intensity emission mapping out one of these lines here. But rather than following this path, what happens is we just get a bright emission in the middle here. This is for a hole density of 0.05 holes per unit cell. This is 0.1 per unit cell. This is 0.12 per unit cell. And you can see that we just get a bright band here on these corners. These are so-called Fermi arcs. And so this was regarded as being another signature of the exoticness of cuprates, that we didn't see the complete Fermi surface when we do an ARPES measurement. So the question is this real? Does it signify exotic behavior? And to try and understand this, we turn to our user facility where we provide high magnetic fields. So what can a high magnetic field give you if you have a metal? Well, we've already said that the velocity of a quasiparticle, an electron or a hole in a solid, is given by this three-dimensional equivalent of the group velocity formula, the gradient in K space of the energy. To get the motion in a magnetic field of this, we just put this into the Lorentz force equation. Rather than being a conventional acceleration here, this is now a rate of change of the K quantum number. So what you can see is that this change is going to be perpendicular to the velocity, and it's going to be perpendicular to the magnetic field. But also, the velocity is perpendicular to the Fermi surface. So if we have a quasi-two-dimensional Fermi surface like this one, and we apply a magnetic field in a certain direction, what we're going to get is an orbit on the surface of constant energy in a direction which is perpendicular to the velocity and perpendicular to the magnetic field. So it's going to give you a cross-section of the Fermi surface in a plane perpendicular to the magnetic field. Now, of course, this is a kind of semi-classical way of looking at things. In fact, the whole thing is quantized, and the correspondence principle means that if we get a frequency of rotation like this, we're going to also get a quantum mechanical energy level spacing. Any closed periodic motion that has a frequency is going to have a quantized energy. And this is in terms of this quantum number here plus a phase factor times the magnetic field over the effective mass. I'm going to get a definition of that in a moment or two. This is just like cyclotron motion of free electrons, except we have an effective mass in there. So this gives us our quantized energy levels associated with this motion. And every time one of these energy levels, which move up as we increase the magnetic field, pops through the Fermi energy, we're going to get an oscillation in properties. That's because the electrons at the Fermi energy determine everything that's going on in the solid. So basically, if we change things around the Fermi energy, we're going to get a change in properties. So for instance, this is the magnetization of a metal looked at as a function of a fairly high magnetic field, and you can see that the magnetization is oscillating. So let's look at a substance that's fairly similar to the cuprates, but which was well known to have a Fermi surface beforehand. And this is an organic metal. It's got a mouthful of a name, but it's a very simple substance. It's a quasi-two-dimensional superconductor. This is its Fermi surface and Brillouin zone. This is the unit cell of K space. We have a closed section of Fermi surface here. Now remember, every time we have a closed section of Fermi surface, a closed orbit gives us one of those frequencies. Therefore, we get the quantized energy levels. And every time one of these energy levels pops through the Fermi energy, we get this oscillation in properties. Here we've got the resistance as a function of the magnetic field. The thing starts off a superconductor, goes into the normal state, and then we get these oscillations. The first thing that you can get out of these oscillations is that they're periodic in 1/, magnetic field, and the frequency of the oscillations in Tesla gives you the cross-sectional orbit, cross-sectional area of this orbit, cross-sectional area of this Fermi surface section here. So without any other assumptions, we can straight away measure the cross-sectional area of the Fermi surface from these oscillations. The second thing you'll notice is, as we jack up the temperature, the oscillations start to go away. The reason for this isn't scattering, it's just to do with the Fermi-Dirac distribution function. At absolute zero, the Fermi-Dirac distribution function is just 1 out to the chemical potential, which is equal to the Fermi energy at absolute zero, and then it drops like a stone to 0. So the Fermi surface is very sharp. At higher temperatures, the Fermi surface gets curved off by a broadening which is about of order the temperature. So as you raise the temperature, the Fermi surface stops being a sharp-like thing, it's a fuzzy thing. So rather than going through a sharp entity in K space, the energy levels are now going through something fuzzy, which is why the oscillations drop off in amplitude. But this is a nice thing because we can compare the energy level spacing, which you remember depended on the effective mass, and the temperature, and we can get the effective mass out of this. So now we want to go on to the cuprates. We want to attempt to measure the cuprate Fermi surfaces using these quantum oscillations of the properties. So first of all, because the high temperature superconductors have these high critical temperatures, they also have very high upper critical fields. And to measure the properties, you remember from the organic superconductor, we need to get it into the normal state. So we need to use very high magnetic fields. The easiest way to get a high magnetic field is to use a pulsed field magnet, a thing like this here. This is a magnet that will give you a waveform in magnetic field versus time that looks like this. Peak field of about 65 Tesla, a duration of about 20 milliseconds. Now, the single crystals that we want to use for these experiments are small. This might sound like a disadvantage, but it's actually very good from the point of view of inductive heating. If you put a metal in a changing magnetic field like this, it will heat up because of eddy currents. That's a bad thing if we want to see these low temperature quantum phenomena. So it's good that the crystals are small, but it's bad from the point of view of putting contacts on them. So what I do is I use a contactless method for measuring the conductivity or penetration depth. Here is the sample. It sits inside a 0.5 millimeter diameter coil, and the coil is part of a tank circuit. It's got a capacitor in there. A tank circuit has a resonant frequency, and so any change in something like the inductance of this coil will result in a shift in frequency. Now, if the sample's conductivity changes due to oscillations or anything like that, its skin depth will also change. That means that the penetration of the oscillating magnetic field in this little coil here will lessen or grow depending on what happens to the penetration depth. This will change the inductance of the coil, so the frequency at which this thing resonates will also change. Now, tunnel diode oscillators, which are used to excite these things, don't like changes in bias voltage. So what I also do is I make a replica of this coil, which is counter-wound. It's the exact opposite of this coil. The reason for that is this pulse magnetic field causes a big induced voltage in here. this one cancels it out, so that the bias circuit, which is driving the oscillator, doesn't see that. Anyway, any changes in conductivity of the sample are going to be manifested as changes in frequency of the circuit, and we can collect data fast enough so that we can do it all in a pulse magnetic field. So here's the very first measurement of a cuprate done in a pulse magnetic field with evidence for quantum oscillations. It's something I did about a year ago on yttrium, barium 2, copper 4, oxygen 8, the so-called 1248 compound. What you notice first of all is this is frequency, this is magnetic field. We sweep the magnetic field up and the frequency follows one path, then it goes on to here. Then we sweep the magnetic field down, it follows the same path, and then the paths diverge here. The reason is that the vortex motion in high temperature superconductors is extremely lossy and has lots of lazy kinetics associated with it. It relaxes slowly. So on the upsweep, basically you get a lot of slow exit of vortices from the sample, slow entrance of vortices to the sample, and a lot of heating caused as a result of that. Here, the sample finally stops doing that. It stabilizes its temperature. On the downsweep it's at the same temperature, and then here it's at a lower temperature than it was on the upsweep. So we have up, relatively hot, temperature stabilizes, down, looking relatively cold. So what we have to do now is look at this small part here and see what we can see in the normal state. This is the normal state of the superconductor. And lo and behold, this is raw data. These are raw data with the background subtracted. This is the frequency. You can see that the frequency and therefore the conductivity is oscillating with the Shubnikov-de Haas oscillations. But we only get 2 oscillations in this particular superconductor, which means that we can't estimate the frequency very well, nor do we have much leeway in doing things like temperature dependence that we can see the effective mass. So to get around this, we turn to our biggest magnet at the moment, I mean biggest in terms of volume, which is this thing here. It's the 100 Tesla multi-shot magnet. Presently we're running it to 85, it will go to 100 Tesla at the end of the year. How does this work? Well, we have a big grey coil here, which is driven by this motor generator set here. There's a person, a fairly large person, standing by the motor generator set there. I think you can see her. We run up to full speed with this thing and then basically short circuit it via some control electronics into this magnet. And that gives us this rising profile here of field versus time. Then at peak field, we have this little thing here, which is a capacitor-driven magnet. You can see it compared to a human being there. That's the black thing in the middle. We connect it to a capacitor bank charged up to 13.5 kilovolts, and that gives us this spike of magnetic field on the top. This is an enlargement of the center. So those two together presently give 85 Tesla. After some modifications to the inner magnet in the autumn, they will go to a full 100 Tesla. There's a human being by the top of this tank, so you can see the scale of this again. Now, using the same substance, we can now see a further 20 to 25 Tesla. Remember that the generator drives the magnet in the first part of its pulse, and it does this over a relatively long pulse time. This is about 2 seconds here. Now the superconductor's vortex motion has time to relax and cool down as it's going up. So the upsweep of the magnetic field and the downsweep follow virtually the same course. Then the capacitor bank driven magnet kicks in, and we go up here and we're into the normal state. When we do a background subtraction, now you can see that we have several oscillations and we can work out a frequency fairly accurately. This is a frequency. Remember, these things are periodic in 1/, so frequencies are in Tesla, and this corresponds to an area of about 2.4% of the Brillouin zone cross-section, 2.4% of the unit cell in K-space. We can also, now we have this big range of magnetic field. This is plotted in 1/, magnetic field, so that you can see these things are periodic in 1/, magnetic field. We now have this big range of magnetic field, so we can look at the temperature dependence of the oscillations and heave out the effective mass. Why is the effective mass important? Well, a brief explanation. This is 2 simple bands, one with a heavy effective mass, one with a light effective mass. So there's the simple dispersion relationship. I'm sorry, the bar has fallen off the H bar in going from Unix to Windows, but what else do you expect? So you know that in K-space, there is a constant density of states, a constant number of states per unit volume of K space. So if you look at this region of K space here, and we look at the light effective mass band, you can see that this width of K space occupies a big range of energy. That means the density of states is low. If we look at the band with the heavy effective mass, this same width of K space, wave vector space, occupies a narrow range of energy. It has a large density of states. So a large effective mass means a large electronic density of states, which means it's important to know if you want to do a model for superconductivity. Anyway, there are several different ways of evaluating the temperature dependence of the oscillations. We can look at a Fourier transform as a function of temperature, which is this thing here as a function of temperature plotted out. We can also do a direct fit of a sine function to the oscillations, which is this one, and both of them give the same answer. We have an effective mass which is 3 times the mass of a free electron. So heavy, but not especially heavy. Now, while this is going on, there are other measurements being made of quantum oscillations in the cuprates. These are some done in Toulouse by a former student of mine. This is the Hall conductivity of a different cuprate. This is the 1236.451 cuprate, but still it's a 2-dimensional Hall-doped superconductor. You can see once the Hall effect gets through the upper critical field of superconductivity, we again see these oscillations here. Slightly lower fields because this thing has a lower critical field. And they measured a frequency which is similar to ours, 520. Remember, it's a different composition though, so it's somewhat lower frequency. And they measured a relatively low effective mass of 1.8. Later this has been retracted, the effective mass, because if you plot a comparison of the irreversibility fields, these hollow things here that they get, with the irreversibility fields which were measured in a quasi-static magnetic field, which are the solid points here, you can see that they're considerably lower. And the reason is that there's a lot of sample heating going on. This region again has this lossy kinetics, and because of the experimental system that they use, which has the sample in low pressure helium gas, the cooling is not very efficient. So this has given us, you've got a high temperature here, and this has skewed the effective mass. As we'll see later, you actually have a heavier effective mass. Then I and several other people at Los Alamos has studied a different composition again. Remember, by changing the oxygen doping, you can change the Hall doping. This one has quite a low critical field. Again, you get the hysteresis between the upsweep and the downsweep because of the lossy kinetics, but up here we get very efficient cooling of the sample. And you can see here the oscillations relatively prominently in the raw data above 45 Tesla. Notice that there's the series which is about 500 Tesla in frequency here, and they're superimposed on a slower background frequency. Remember that every frequency you get corresponds to a cross-sectional area of the Fermi surface. So that means that the Fermi surface has 2 cross-sections, one of which is smaller and one of which is slightly larger. So to look for more evidence of that, we also went to the Tallahassee High Magnetic Field Laboratory and used a thing called a torque magnetometer to see if the oscillations were also present in the magnetization. This is basically like a little springboard made out of phosphor bronze with the sample on top of it. There's the sample. There's a Bic biro pen. When the sample's magnetization changes, the torque on this cantilever changes, and that changes the capacitance between this ground plate here and the springboard. And it's a very, very sensitive method of getting out magnetization. And lo and behold, in the torque, once we've subtracted the background due to the fact that we're in the mixed state of the superconductor, you again get these oscillations of a low frequency. Are these lower frequency oscillations present in the other dopings of cuprates? This is again back to the 1248 cuprate. These are now the high frequency oscillations we saw before. You can see them here. If you do a different sort of background subtraction than the one we originally did, you can see that they're superimposed on a lower oscillatory frequency as well. And indeed, in the very first Fourier transforms, this is something that was scanned out of my logbook and labels typed on later. This frequency, this lower frequency, is also present. So it looks as though you have a low frequency of about 200 Tesla and a higher frequency which is between 500 and 700 Tesla in the various dopings we've seen. Finally, colleagues of mine looked at the doping that the Toulouse people had studied again. This is the 1, 2, 3, 6.51 cuprate in the hybrid magnet at Tallahassee, and they did torque magnetometry again. These are the raw data. If you look very carefully at these, do a Fourier transform of the data, you see the frequency that was seen before at about 500 Tesla. There's an additional blip over here at about 1600 Tesla. Now, in the raw data, even with a very careful background subtraction, it's very difficult to see this frequency. There's one of the oscillations here. But if you take out the lower frequency, the 500 Tesla one, which are these prominent oscillations, you can see you get left with a further series of oscillations which have a frequency of about 1,650 Tesla. These are seen in some of the other dopings as well. This is the 1, 2, 3, 6.6. These are just taking raw data. This is the sweep of a different pulse magnet, this time the 55 Tesla long pulse magnet at Los Alamos user facility. These little arrows here correspond to the arrows that you can see when we blow this section up. And I think you can see that there is an oscillation there, and it's of a frequency of about 1,890 Tesla. So it's about time for a summary. As we change the oxygen in these various different cuprates, we're increasing the number of holes that there are. So we would expect the Fermi surface, as the number of quasiparticles to grow, to get bigger. We would expect the frequencies that we see to get larger. And these are the frequencies that have been seen in the various experiments that have been done so far. Not at all logically, they're called alpha, beta, and gamma in not increasing order of frequency. It's in increasing order of discovery. So as you can see, there's this 500 Tesla frequency in the low doped one, which grows to 550 Tesla as we crank up the holes a bit, which grows to 670 Tesla as we put more holes in still. There's this low frequency that I pointed out, which was just seen as a kind of background, which seems to stay around 200 Tesla, although it's very difficult to get an accurate frequency in spite of what's quoted in these various preprints and papers. And then there's this high frequency, which is discovered in these top two, which has been inferred from the way in which the other oscillations behave in this third one here. And again, this is increasing as you go up in hole doping. Now, why is this important, this high frequency, which produces very weak oscillations? The reason is that it's got heavy effective masses and it's got a large area. And if you include this one, we can account successfully for the electronic specific heat of these cuprates. By counting these three sections of Fermi surface, we have enough holes to deal with the electronic contribution to the specific heat of the cuprates. So in other words, we think we've detected everything there is to detect. So you will remember that when I first mentioned these things, they correspond to a few percent of the Brillouin zone, a few percent of the unit cell cross-section in K-space. This is about 2.7%, this is about 6%, about 7%, 8 or 9%. So how does this compare to the calculated Fermi surface? Well, this is the original calculation of the Fermi surface. Very simple thing, approximately square. This is the unit cell of K-space here. So what's happening to produce these smaller, much smaller Fermi surface sections that we detect in the measurements? Well, what's actually happening is that there's an additional periodicity in the system. Now, if you impose an additional periodicity in real space, what that does is it gives you an additional periodicity in K-space as well. So if you make the real space unit cell bigger, we have to make a smaller unit cell in K-space, like this black one here. And it turned out there are already a lot of proposals that this sort of Brillouin zone would actually exist in the cuprates because of things like incipient antiferromagnetism. These were made in the early days of the field. So where is this coming from? Well, here's a very simple example of the sort of thing that drives these sorts of transitions. A Fermi surface instability. This is a one-dimensional system that I've pictured here, just to make things very, very easy. On the left-hand side, we've got our simple band here, like this. And here is the Fermi energy. This is a so-called half-filled band because there's one electron, the black blobs, per atom, which are the white blobs here. And the electrons are happily moving around in this band and doing stuff here. Now, it actually happens that the system can lower its energy quite significantly by distorting itself. Now, this doesn't have to be a structural distortion like the one I've shown here, but let's take this simple example for the time being. Supposing it does a distortion like this, it now has a new periodicity in real space. Notice that the size of the unit cell in K-space is given by 1 over the size of the unit cell in real space. So we make a smaller unit cell in K-space. That has the effect from elementary solid-state physics of opening up a gap on the Brillouin zone boundaries due to Bragg reflection. And what's happened then is that all of the electrons that were populating this lower band have managed to lower their energy because of the opening of their gap. And this is actually a stable thing. This mechanism means that one-dimensional metals cannot be metallic at absolute zero. They're all insulators. But it also happens in more complicated systems as well. This is a Fermi surface of an organic metal that we looked at a few years ago. Here it has two parallel sections like that. It turns out that if you can get a vector, a distortion that has a wave vector, a periodicity, in other words a 1 over periodicity, which can map one part of this onto the other and wipe out quite a lot of states, the system can lower its energy that way. And this is what happens. Once you do that, once you map this onto here, the system can lower its energy by wiping out all of these states. It's opening up this gap. But you've introduced a new periodicity into K-space. That means that if you take anything that's remaining in K-space, it has to be mapped all over K-space by this periodicity. So we take this thing here and we map it all over K-space, and it gives us a right mess of a Fermi surface. But you can see that the general principle is that if you have one of these distortions, it tends to give you smaller sections of Fermi surface than the original ones you started with. This is a blow-up of that region, and you can see that the original large piece of Fermi surface has been changed into all these little bits by one of these distortions. So what was happening in the cuprates? Well, let's suppose that you have some sort of distortion. The distortion need not be structural, it can be magnetic, like an antiferromagnetism, and we get this new Brillouin zone. Well, we get gaps opening along the Brillouin zone boundary. We have a replication of this part of the Fermi surface in here, and these gaps and this replication result in little Fermi surface pockets like this. And this was a proposal by Steve Julian and Mike Norman after the first measurements were published in the middle of last year. So we have little pieces of Fermi surface due to the antiferromagnetism introducing a new periodicity into the system. Now it turns out that to replicate our Fermi surface, the thing that we actually measure with its three different pockets, alpha, which was the 500, 600, 700 Tesla one, beta, which was the 1500, 1800 Tesla one, and gamma, the one which was responsible for the low frequencies, you have to propose quite a complicated wave vector for the distortion. But it turns out that this wave vector is seen in neutron scattering measurements. It's seen in antiferromagnetic scattering, and it's an incommensurate antiferromagnetic wave vector. It means that the antiferromagnetism has a different periodicity than the real space crystal does. And that gives us this new K-space periodicity, which gives us a mapping of the original Fermi surface to create the thing that we actually measure in the measurements. And these pockets match up with our data very well in size. They also, again, give you a good calculation of the electronic specific heat. So this is our best guess based on the data from neutron scattering and from our Fermi surface measurements as to what the Fermi surface of the cuprates actually looks like. So as time is going on, I think I'll just go through these quickly and then go on to this part as to how we can reconcile this picture with the ARPES experiments. You remember that the ARPES experiments were trying to map out this region of the original proposed Fermi surface. They were going along here in K-space, but they were just seeing these brightly coloured blobs like this in K-space. So how does this square with the pocket that's the leftover, this one, from that piece of original Fermi surface? Well, we can try to understand that by modelling what's actually going on in making this new pocket out of the original band structure. So here is the original Fermi surface, the electronic band, in a simple model, this thing down here. When we introduce the new periodicity due to the antiferromagnetism, we basically introduce a new plane about which we've got to reflect the Fermi surface. This is this wave vector given that I mentioned before, the Q that I mentioned before, to produce the new Fermi surface. So this point here is just taking a diagonal like this and reflecting the original piece of Fermi surface in it to make the new Fermi surface, which is the white pocket that you see there. Now the neutron scattering measurements show that this fluctuating antiferromagnetism has a very short correlation length. That means that if you measure it in one place, it has a different periodicity than in another place. If you measure it in a third place, it has a different periodicity still. There's a kind of distribution of these periodicities. So what effect would that have? Well, if we have a slightly different periodicity, a smaller periodicity in real space corresponds to a larger distance in K space, so it means pushing this boundary out slightly. We then end up with this red pocket here. So let's suppose then that the neutron scattering measurements are telling the truth, and we have a distribution of these different periodicities in the antiferromagnetism, so that we get not just the white pocket, but we get the red pocket in some places, and see what effect that what that has. So basically what we do is we propose that there's a probability distribution of the different shapes of Fermi surface resulting from the moving in and out of this blue dotted line, which is given by the correlation length seen in the neutron scattering measurements. What this is going to do is, look, the original part of the Fermi surface doesn't move very much as you move this blue dotted line around. But on the other hand, the new part that's made by reflecting this original part does move around a lot as you move the periodicity of the antiferromagnetism around. So let's have a look what happens when we impose this probability density onto the reflection, which gives us the different Fermi surface areas. So this is manifested in terms of a correlation length. If you have a long correlation length, basically the antiferromagnetism looks pretty uniform. And now this is a simulated ARPES measurement. This is a simulation that we've done just by looking at the number of states at the Fermi energy. With a long correlation length, basically there's not much variation, not much statistical variation in the size of this thing, so the Fermi surface just looks like one pocket produced by this reflection. And indeed the simulated ARPES measurement looks like that. As we start to reduce the correlation length, the side of the Fermi surface that's created by reflecting in the new periodicity produced by the antiferromagnetism starts to go all blurry. As you reduce the correlation length further to 20 angstroms, we get this side being almost completely wiped out, and as we reduce it further to 10 angstroms, then all you see is the original piece of band structure that gave rise to the first side of the Fermi surface. So in other words, the statistical variations are wiping out this bit that's caused by reflection and leaving this bit here. So this simulation, which is done just using our measured Fermi surface and that statistical model, looks very much like the ARPES data that people like ZX Shen get. And this is using a very similar antiferromagnetic correlation length to that measured in the neutron scattering. So we think we can understand the ARPES data. We can even model, this is our model of the intensity that you get as you rotate the wave vector across that piece of Fermi surface. Remember, this is the model and this is a representation of the various different data sets. So all of the features of the ARPES data can be reproduced by assuming that you have rather disordered antiferromagnetism, which is giving rise to these small Fermi surface sections like this one. So finally, in the last sort of 5 minutes or so, I'll see if this can give us something that might be taken as being a model for cuprate superconductivity. So remember that I mentioned that the neutron scattering measurements picked up this incommensurate, which means it doesn't have the same periodicity as the real space lattice, this incommensurate antiferromagnetic scattering. And this is the sort of thing that the neutron scattering measurements see. As you look at the scattering energy of the neutrons as a function of wave vector, you get these dispersion relationships which are from the antiferromagnetic scattering. And for different hole dopings, these are 0.5, 0.4, 0.2, 0.05, you get different dispersion relationships. Now, where these things touch ground at zero energy is telling you about the new periodicity in the system. This is the periodicity that's giving rise to that Fermi surface reconstruction that I showed you earlier. It's the thing which is involved in breaking the Fermi surface up from its big state into the small pockets. And this periodicity down here, it's in K space, translates to a real space frequency, which gives you the Fermi surface. So this is the sort of dispersion relationship that the neutron scatterers measure. And it's parameterized by this item delta on the bottom here. And the delta is basically a measure of the spread that these things have when they touch ground. Now, what we have to do is to be able to simulate the neutron scattering. These are simulated neutron scattering data with scattering intensities, red being intense, blue being low intensity. And you can see once we look at this thing in 2 dimensions, you're getting peaks corresponding to these regions where the dispersion curves touch down at these points here. Not at 0 wave vector, but out in the Brillouin zone. So what we have to do is to be able to simulate these neutron scattering data, and we do this using a static spin distribution, which has got, again, this correlation length in it, xi, and which gives us something that reproduces the scattering amplitude that the neutron scatterers get. And this is a functional form of that. The intriguing thing about this is the functional form of the spin density that gives us that neutron scattering. It looks very, very like the D-wave Cooper pair wave function. This is the D-wave Cooper pair wave function plotted in real space. This thing up here. It looks even more like it if we take this and transform it, Fourier transform it in 2 dimensions into real space. This is what you get when you take the spin distribution and plot its real space distribution here, and you can see that you even get the same phases of spin distribution as the D-wave Cooper pair wave function has. So that was very interesting. So our next thought was, well, if the spin distribution that gives you the neutron scattering in the Fermi surface looks so much like the Cooper pair wave function, perhaps they're linked in some way. So what we did was we took this parameter delta from the neutron scattering data, and we plotted out the neutron scattering susceptibility, and then we plotted out the real space spin susceptibility that gives you these scattering amplitudes here. That's the real space representation of the susceptibility that you get from neutron scattering. So notice as k space gets bigger, real space gets smaller because they have a reciprocity relationship between them. The next thing to do is to take completely independent data for the coherence length of the superconductivity, and this is measured thermodynamically from things like magnetization. The coherence length is this thing here. It comes into the Cooper pair wave function in this exponential term here. And this is for different hole dopings. This is 0.06, 0.10, 0.152. These are neutron scattering data, or inferred from neutron scattering data. These are the Cooper pair wave functions plotted using thermodynamic measurements of the coherence length. And you can see that with no adjustable parameters, these things match very well. As you increase the hole doping, the Cooper pair wave function gets smaller. As you increase the hole doping, the spin susceptibility distribution gets smaller as well. And these things match up rather well. Remember that the data that went into drawing this are completely independent of the data that went into drawing this. And these are for these 3 separate dopings. So if you look at these 2 representations here, you can see that the length scale of this one is given very much by the coherence length. The length scale of the other one is given by this parameter delta here. So it should be, by looking at the maxima in spin density and the maxima in probability density, possible to see what would be the condition for matching these 2 things up. And it turns out that the condition for matching these 2 things up is that the coherence length divided by this parameter d is just 3/2. That's this green line plotted here. Now this parameter d is just the lattice parameter divided by the thing delta that we measure from the neutron scattering data. So this is theoretical expectation if it's a matching between the spin susceptibility and the Cooper pair wave function that's giving us rise to the superconductivity. These are experimental data. And remember that this parameter is determined from neutron scattering, this one from thermodynamic measurements. These are independent measurements of the 2 parameters. The square points here are for IBCO, yttrium, barium, copper oxide. The round points are for LASCO, lanthanum, strontium, copper oxide. And you can see that they all lie very, very close to this line, which is reasonably remarkable, I think. So you can even look at the plot of delta, which is the parameter again which determines the coherence length, and the coherence length to the -1. Remember, this is a theoretical link between the 2, and they follow the same sort of behavior but skewed a little bit as the superconducting transition temperature does. So obviously, well, I think obviously anyway, these antiferromagnetic fluctuations that give rise, which are caused by the spin susceptibility, are very closely related to the superconductivity. So in summary, I think that measuring the Fermi surface has opened up a whole lot of opportunities in these cuprate materials after about 20 years of you know, relatively stalled theoretical comprehension. So we've observed Shubnikov-de Haas and de Haas van Alphen oscillations in cuprate single crystals. Because we've observed these two things, these oscillations in the conductivity, it means that cuprates possess a Fermi surface. Cuprates are, in many respects, like conventional metals. We see these small Fermi surface pockets here. There are areas that should say 1 to 7% of the Brillouin zone area. And this can be understood in terms of a Fermi surface reconstruction due to this antiferromagnetism, which is breaking the original big Fermi surface up into these little pockets due to the new periodicity that's introduced into the system. By counting these pockets up and their effective masses, we can account for the electronic heat capacity. We can also account for the ARPES data by looking at the effect that the antiferromagnetic fluctuations have on the sizes and shapes of these things. So we can understand the Shubnikov-de Haas oscillations and the ARPES data using a single model. And I think because the antiferromagnetic fluctuations are obviously so closely related to the Cooper pair wave function topology, we have the beginnings for a model for superconductivity here in the high temperature cuprates. And it's not so exotic. It's basically something that is a metal with a relatively conventional Fermi surface in which there are strong antiferromagnetic fluctuations of a particular geometry, fourfold symmetry, that map on to a D-wave Cooper pair wave function. And so, you know, I'm an experimentalist. I don't think I can go any further than that. I'm hoping that a theoretical person will take the baton and run with this further. So thank you very much.
Do you want to do the questions? Or?
Yes, certainly. Okay, thanks. Thanks very much indeed, Carl. I think it'll be interesting for people to review the talk, you know, on the web later. We're very grateful to you, and I think there's a lot of instructional stuff. I learned something there about magnets and superconductivity. There is obviously time for questions. Has anybody got anything they'd like to ask John at this point? Yes.
You show us quite a lot of good example about hole doping.
Yes.
Is there any example about electronic doping coverage?
At the moment, the crystals for the electronic doping side of the phase diagram don't seem to be quite as good quality as the hole doped ones are. If you know of a source of good single crystals of the electron doped side of the phase diagram, then we would be delighted to try to measure oscillations in them. At the moment, there are sample quality issues which are preventing us from seeing oscillations in those materials. But the hole doped side of the phase diagram, the sample quality still continues to improve. So my hope is that, stimulated by experiments like ours and the ones the Toulouse group are making, people will clean up the electron doped side of the system. But if you have some samples, come over and do an experiment. We'd be glad to have you.
There's a good invitation. All expenses paid, I'm sure.
We can give you up to $1,200 if you're a first-time user, which will pay for your flight and a sizable proportion of your accommodation.
I would take that up.
Yeah.
Any other questions?
One over here.
There are loads of different areas that you've conveniently ignored.
Oh, of course, yes.
If you take lanthanum and barium cuprate, it suddenly becomes not a superconductor at 0.18.
Right. Well, my take on this is that there are a lot of other oxides, nickelates, rutheniates, that Bill Hayes and I looked at in great detail a long time ago, where you might expect that if you have these fourfold symmetric planes and a similar sort of Fermi surface to the cuprates, they would also superconduct. And in fact, they don't superconduct. They do stripes and checkerboards and things like that. My belief is that for this method of superconductivity to work, the electron-phonon interactions shouldn't be so strong. If they're any stronger, what will happen is you'll have something like a charge density wave rather than a spin density wave, and that will act in competition with the superconductivity. So all of these other materials like nickelates have stronger electron-phonon coupling constants, and so you get checkerboards and stripes, which are basically, I think, in spite of the differing terminology, they're charge density wave-like phenomena, which get there before the superconductivity does. And the cuprates are mostly of a sort where the electron-phonon coupling is not so strong that it gives you an alternate ground state at low temperatures to this one. But in some of them, the electron-phonon coupling constant is a little bit higher, or you're at some sort of commensurability where the CDW can lock on very, very stably, and then the charge density wave-like order, the stripe or checkerboard or whatever, will win, I think. I think it's a delicate balance in the cuprates.
But even in the yttrium-bearing cuprate, there's evidence for stripes.
At certain filling factors.
No, but other ones, it's just they're more dynamic rather than static.
Yes, and you would expect, because there's that they will be related in some way to the dynamic antiferromagnetism that you're seeing, because there's a strong magnetism charge coupling. You know, because of the on-site Coulomb correlation energy, you'll get a strong coupling between the magnetism and the charge order, which is why you know, antiferromagnetic fluctuations have an influence on what's going on with the electrons. So you would expect that anything that has a periodicity tied up with it in the magnetic system would also have a periodicity in charge, which you can pick up.
And I thought all the debate was not whether the cuprates in the superconducting state at high magnetic field were Fermi-like, but that the non-Fermi liquid area was in the T-star area, slightly above the temperature of the superconductivity bubble in the underdoped region.
Well, yeah, but if we can go back.
And if you go back and start explaining that actually cuprates are fairly standard metals, then that's...
So you're a convert, right? Okay, let me let me just. So people know what he's talking about. I'm sorry, I should have gone into Slide Manager or whatever it's called. What he's talking about is that there's an idea that this T-star thing here is in some way separating a funny thing. Which is not a Fermi liquid, a non-Fermi liquid, from a Fermi liquid up here. Now, you can. Now, if that were the case, you have to say, why is it that we see a smooth, without any histrionics or odd behavior, smooth transition from superconductivity into the metallic state? Which gives us the quantum oscillations, and even why, in the case of the magnetic field measurements we did at Tallahassee, we see quantum oscillations of the same periodicity within the superconducting state. You know, where is this? If this is an exotic state, where has it gone to? Because within the superconducting state, you can see quantum oscillations. You crank up the magnetic field, the thing smoothly becomes a metal. The quantum oscillations don't change frequency. Nothing surprising happens. So my view of this will be more like that of sorry, this is what happened when you jet lagged. I've forgotten the name of the guy, but he's at the University of Tennessee, theoretician, and he's working on this in terms of a sort of Landau theory where this is an inhomogeneous mixture of various ground states, and the metal. The dilute metal is in there, being conventional metal, but it's got magnetism and charge density wave-like things mixed up in there as well. But I can see in my quantum oscillation measurements, there's no evidence that the superconducting state or the mixed state is anything funny, really.
All right, well, let's join and thank John very much for the talk, and we'll take it.